Hello, everyone. My name is Devendra Kapadia, and I'm the manager of mathematical computation at Wolfram. It's a great pleasure to present this talk on what's new in mathematical computation to you today. Now, mathematical computation is a pretty big area of the Wolfram language. It includes all of symbolic and numeric computation. And in this talk, I'd most like to focus on some new and exciting features coming up in version 14.2. I should say that there have been probably around 10 talks related to the team's work at this conference, and I invite you to either watch the recordings of those talks or attend the ones that are going to be live later today. But these are exciting times for us, and I hope that you'll agree with me that 14.2 is a wonderful release for us. So let me begin with the plan for my talk. So I'm going to discuss new development related to a few areas, and perhaps the most exciting and new development is the game theory. This is a vast area. I'm certainly not a game theorist, but the reason why I took it up is that the so-called Nash solver, which many of you have heard of, is a piece of polynomial equation solving. And then from there, we have tried to build a beautiful set of functionality which people can use to study game theory. I'll only give a brief glimpse of it, but there'll be another talk this afternoon to actually give you more details. But this is kind of a new direction for us. The other areas, more like array algebra, but I'm going to focus on symbolic matrix algebra, which is a special case because I think that's been requested by users for a long, long time. We have done polynomial algebra in 1988, some fantastic tensor algebra in the 2000s, and now we have array algebra to almost wrap it up. We have a bit more, but I think this is a kind of landmark for us. A third area which now falls under team is actually an industry, it's not an area, and that's PD modeling. And there were several nice talks on it already, but I'll take up just an example from one of the new features in 14.2, which is magnetic field modeling. And I hope that you'll see how useful this whole functionality is. Of course, core calculus is a staple thing for us. So we have some improvement for array calculus using arrays and calculus solvers, improvement for the sum convergence function, and improvement for the documentation and numerical evaluation of Fourier transforms, a very well used area in the system. And finally, I'll briefly touch on GPU computation. I'm certainly not an expert over there, but I'll focus on that part, the part related to linear algebra, which I was kind of involved in developing for the last couple of years. But this is kind of an exciting new direction for us for the future. So this is really future functionality. Some of it might be in 14.2, but I think of this as the next 5 or 10 years work for us. And finally, as an education team, we have been working on books and courses. That's a pretty active area for the team. We are a team of scholars, writers, and I think this fits perfectly with our mission. Okay, so without further ado now, let me take up the first feature for today, which is game theory and matrix games. So matrix games are a special class of games. They are simultaneous moves, so there are 2 or more players, they have 2 or more actions, and they just have one shot. So they're called one-shot games. And the new function matrix game will let you do that in 14.2. So here is a matrix game. It's a 2-player game with each action, 2 players having 2 actions each. And those numbers over there are what are called payoffs, the end results of the game. And you can understand a bit more over here. It's a zero-sum game. So one player's gain is the other player's loss, etc. Okay, so that's the situation. You've got 2 players, 2 actions each, and if you like plots, we have a nice new function called matrix game plot, which will actually plot the game using bar charts. So these bar charts over here, you can see they're flipped in each case because it's a zero-sum game. Then you might say, okay, all that is good, but what's the optimal strategy, optimal strategies? So then we have a beautiful new function. This is where the algorithms come in, find matrix game strategies, which will actually find the optimal strategy or strategies for you. In this case, we have actually probabilities. they add up to 1 for each player. And one important thing is, how do you know the answer is right? There's no intuition really for these things for most people. So we have a function called verify matrix game strategy, which will let you actually check that the answer from the earlier output was actually correct. So I've shown you how to set up the game. I've shown you how to plot it, solve it, check your answer, and finally, that's what really matters, what you take home if you win, and that's the payoff for each player, which comes from the matrix game payoff function. So that's a really simple, almost trivial workflow for this new piece of functionality. Now, matrix games are, of course, somewhat easy to work with, but a slightly harder class of games are the so-called tree games, where the moves happen in sequence, and sometimes they're called game trees. So really, these are game trees. So a tree game is a game in which you got 2 more players, they act in sequence, and of course, things can get really, really messy with this. So the best way to do it is to work with graphs. So here's a tree game with 2 players, A and B, and you can plot the game. So you had matrix game plot over there, you have tree game plot over here. You can solve the game. You got find matrix game strategies over there. We got find tree game strategies over here. Find the strategy, the optimal strategy, verify it's correct, and find the payoffs, the expected payoffs for each player. So together, the matrix game functions and the tree game functions are going to be quite valuable for starting us off in this very deep and important area of economics and all that. But our real concern was, how do people start off with this game theory functionality? And so we have game theory data, somewhat like the entity framework, but more localized to game theory, which includes a collection of around 50 classic games. And if you can't find a favorite game over here, let us know, we'll try and put it in. So these are really simple games which you might even have played if you're a game player. So you look at the list over here, arms race, beer quiche, etc., and you tell yourself, okay, I think I like rock, paper, scissors. So you pick a game, rock, paper, scissors. Here's what it looks like. That's the cover slide. Now, if you, like me, didn't play rock, paper, scissors when you grew up, or didn't know you were playing it at least, then you might ask, what's this game all about? So then you can obtain a description of the game. So you see game theory data, rock, paper, scissors, description, and it'll tell you what this game is all about, who wins, depending on whether they play rock or paper or scissors. Now you're just trying to learn the game, so you say, okay, where do I find more information about the game? So you can find the source of the game in this DY link, and it might tell you that this game started off in China, but then the modern form was due to Japan, etc., etc. And then you get a bit more technical and say, okay, but what kind of game is it? Classify it. So it's a 2-player game, rock, paper, scissors. It's surely a fun game, not be played at work or whatever. It's a zero-sum game, and it's so-called intransitive, but the most important part is it's a matrix game. So now you can take the same game theory data and put the game name over here, and you get back a matrix game, and then you can play the same game all over again. No pun intended. Okay, so new functionality in our eyes is intended to be useful for learning game theory, not necessarily for actually, becoming an expert on it straight away. You might, and one day a student might win a Nobel Prize in economics. That's great, but we really are not there yet. Okay, another important area, array algebra. So we had array calculus in symbolic arrays and array calculus in version 14.1, and now in version 14.2, we have array algebra. And there are 3 functions, very simple functions. There is component expand, and that just expands an expression, a vector array expression into components like this cross product over here. We have array expand, which is the analog of expand. Expand being there for a long time. So if you expand over here, you have a dot product. That's like the time in the array world. It expands out just like you would in normal algebra. And just like the inverse of expand is simplify, the inverse of simplify is array expand is array simplify, and you get back to where you started from. So component expand, array simplify are the new functions for doing array algebra in 14.2. Of course, we could have overloaded simplify, full simplify, but they are very difficult functions anyway. So we best have a new function for each of these operations over here. Okay, and now to me, the real win over here is symbolic matrix algebra. I mean, I've taught a linear algebra course for Wolfram U, and I wish we had some of the stuff at that time. So the point is, we have actually mined a very large number of matrix identities in 14.2 and put them into array expand and array simplify. So for example, you might say, what's the inverse of the matrix? And of course, you get back the matrix. You might ask the question, what's A dot B dot C transpose? And you get back to C transpose, B transpose. That's always the case, that the operations get reversed, somewhat like putting on a socks and shoes first, and then taking off your shoes first, and then your socks. Okay, the same kind of idea. And of course, you can use array simplify to go back from here to there. And a much more elegant result over here is that if you find the determinant of the matrix exponential, then you get back e raised to the tracer matrix, which might be easiest to see if the matrix were a diagonal matrix. So these identities are available all over the place. If you see one of them, you can just try and check them with 14.2. You don't need to specify A, B, or C. It just works. And I think that this feature is requested for a long time by many users. Yes, we do have tensors, beautiful stuff, but I think we are aiming at people trying to use this in colleges and maybe data science or the fields. Okay, on to PD modeling. A vast area we've been working on forever. It's in version 14.2, what we have is support for modeling magnetic fields along with some stuff on cerebral, etc. But I think this is the key new feature. And so let's try and model a cylindrical permanent magnet. Okay, so you set up the variables, define the magnet region, cylinder, define the magnetization vector, like over here. Now the problem is the method requires you to have a finite volume. So you select a sphere of radius of a large radius around that to be a surrounding volume. And the poor magnet is in this lonely world. It's on its own. It's a large sphere. That's the magnet inside. And if you tell me you can't see it, well, you're not supposed to see it because it's really, really tiny. It's a small speck in this compact universe. You set up your partial differential equations. That's the new function, the PD component. Give a Dirichlet condition with the new potential condition. Solve the problem with ND solve value. And this plot takes a long time, but what you get back is really beautiful. It's a tribute to our Wisp functionality that you get back this very realistic looking picture of the magnetic field. So I think that we have a wonderful kind of piece of functionality over here, and the talks in the conference have also covered other areas like, like I said, cerebral aneurysms and neural network modeling and plasticity. But the core new function over here is for magnetic fields. On to array calculus. And what you have over here is an extension of what happened in 14.1. So in 14.1, we introduced symbolic arrays. And now in 14.2, we are starting to populate their use in various functions. And the obvious one over here is line integrate or surface integrate, which is vector calculus. So you can now use vector notation in line integrate to do your computations. Or you might say, okay, I have a system of ODs and I want to use vector notation. Sure, do that. So things are getting more and more elegant. We've been trying various things, but it looks like at long last we have a framework for doing multivariate algebra. Okay, so I think that what I've spoken about so far is all wonderful, but how about something a little more classical? So I talk about sum convergence. So we introduced sum convergence in version 7 really, and sum convergence was designed to actually analyze only the end behavior of sum. So you have a sum, let's say 1 over n square, from some lower limit to some upper limit, but we just looked at the behavior at infinity, the asymptotic behavior, so to speak. And that was because we didn't quite know how to handle finite singularities. What happens at 0, for example, and in 14.2, you can also specify the interval of summation in sum convergence. So you can now say over here you have a true because the sum converges to infinity, 1 over n square. But now you can say n goes from 1 to infinity, and it will still work for you. It still give back true. But if you say 0 to infinity, well, there's an issue at 0, so you get back a false. And everyone wants to know what about parameters. Well, if you have a parameter over here, then you can say you get back the answer that a is an integer and a is greater than or equal to 1 for the sum to actually converge. So sum convergence took life in version 7. Shortly thereafter, Wolfram Alpha appeared, and believe it or not, they have been pretty big consumers of sum convergence because the Calculus 2 syllabus actually has convergence testing as the main theme, not evaluation of sums. So happily, we have found them to be a good source of suggestions for us, and they asked us for this feature. So thank you very much, Wolfram Alpha team, for helping us to introduce this nice improvement to a pretty important function in the calculus functionality. Okay, on to Fourier transform, which is probably my favorite area of calculus. I've worked on it forever, but now we have other people who work on it, and we've got Juan Ortiz who works on it. So we have new support for numerical evaluation of Fourier transform using basically numerical integration. The Fourier transform is an integral, and we can now integrate numerically as well, which is a big improvement. But what was really missing with Fourier transforms in earlier releases was documentation. We have fantastic documentation of Laplace transform, and the question was, why not a Fourier transform? Well, who would do it? There are 6 functions, but we have done it now. So Fourier transform functions, the Fourier, inverse Fourier, Fourier cos, inverse Fourier cos, etc., now have wonderful new documentation in 14.2. And of course, we could go on with this for some more time, maybe improving the symbolic evaluation, generating conditions, etc., etc. But those are much harder tasks in some sense. We have done the groundwork, which might be what most users wanted from us. And on to a theme which I've actually, I saw this grow, and today it's been taken over by real experts. So we have a significant effort going on to use GPU acceleration in our solvers. And the function that most appeals to me is linear solve, because that's a key function for many things. And you may have seen this in the talk by Ita yesterday, but basically here's a comparison of linear solve, GPU versus CPU, 64-bit and then 32-bit on a pretty powerful GPU and reasonably good, very good CPU. And what you see over here is that in the 32-bit case, you do get some pretty dramatic speed up improvements. So this is a different game from what we normally do. It's performance, so you need to pick the right problem, pick the right machine, etc., etc. But I think this is where the future lies. So I feel that if we can integrate this into our workflow, then we are good, because with the AI revolution, GPUs are now becoming more and more common knowledge to even the lay people. And finally, books and courses. So we have been putting a fair amount of effort into both of these. And the calculus ebook which John Clark and I wrote appeared as an ebook earlier in the year, and the Kindle, a print version was published in July 2024. So that's the first complete book. Many other excellent books coming up on signal processing, number theory, complex analysis, not just from our team. And we're hoping that this program will go on for quite some time. Much more well established is our Wolfram program, but we now have a new complex analysis course which went live recently, by which I mean this week, by which I mean 2.5 days ago. So we actually have now a program whereby we probably will have 15 courses in mathematics and 15 books in mathematics-related areas, which will help students learn the computational way. So the current topics being worked on are Laplace transforms, special functions, PDEs, etc. And all these are actually very much in progress. We should have them ship whatever sometime in the next year or so. So these are really very active, exciting times for us. And for that, I'd like to thank the developers of our team, the people in Wolfram Media teams, QA, our users support us so much. It's great to see that we are able to maintain this flow of ideas, and it's always nice that just pure mathematics basically is appreciated so much by people in the outside world. So that was a very brief talk. There'll be several other talks today by Adam Strisbonsky and Itai Segev on symbolic arrays, and then a talk by Mark Vicuna on game theory, which I certainly recommend you attend because that's a big area. He's an expert. I'm not really a game theorist, but I think that those talks are really good. We have also had several other talks on GPUs and PDs and all kind of stuff, which I strongly recommend you look at the recordings. But it's probably now time to take some questions before we all head to Adam's talk. So let me see if there are any questions at all. Oh, okay. Yes, surely we'll provide the questions. It would be nice if you could share the notebook. We surely will do that. Right. So that is definitely the goal, that after the presentation, we'll have the notebook available to you by a link. Next question, can you calculate Nash equilibria and Pareto? Yeah, so actually those are the underlying, the solvers that we have are using all this technology, okay, the Nash equilibria, etc. But we are a bit more ambitious that we'd like to keep the names of these functions pretty general to allow other strategies as well. So right now, you are getting, in some sense, the Nash equilibria and Pareto optimality strategies, the sub-game perfect, etc. It's actually all in the system even now, okay? But we just don't have new functions which are called those. Perhaps we should have just called them that, okay? Right. So that's a really good question to call in. Okay, is XM so really two-dimensional? Any problem in setting up in two space coordinates only? Oh, there are other, I think we could do that, yes. So question from Harold is, could we have set some two-dimensional thing? Well, I think we certainly could have done that for sure. And Oliver has some nice examples for that. So he might be the best person to contact if you want to do that. We do have an office hour this afternoon, so please feel free to stop by. And one more question from Patrick, which says, can you please explain the distinction between you and Stephen are making when using the word symbolic in the context of vectors? What is the essence of what is new, or how things change? Oh, I see. Patrick, that's a really good question. So here's the problem, Patrick. We could have done symbolic vectors 5 years ago, but there's something called the curse of listability, which means that those vectors would then creep inside lists and destroy whole computation. So the symbolic vectors that we have now are nothing new. They've been around since Newton's time, okay? But what we have avoided now is things like, if you do symbolic vector v plus 1 to 3, then the v does not go inside a list. So it's a pretty technical thing, but symbolic means distinct from numeric. It could become numeric. So we are not like NumPy or whatever. We are kind of our own symbolic world, and we stay symbolic to avoid issues with listability, etc. But that's a good question. Okay, so Oliver already answered. Oh wow, Oliver's here. Okay, good. Oliver answered the question about you can do it in 2D. Yes, in fact, Oliver had some really nice example in 2D, but I like this one a lot. It appeals to my mathematical tastes. Right, question from Arjun. Are the video courses on Wolfram U complementary to the e-textbook, or is the entire textbook available? Yes, so Arjun, we are trying to be as redundant as possible. So if you go to the Wolfram U course, in many cases there will be a tab which says full text. That's the whole textbook which you could get as an e-book. But we know that not everyone comes to the Wolfram U site. So we also have a separate e-textbook with all the notebooks, with some really beautiful stuff from Wolfram Media for flipping through the book and scroll down menus and all that, which are wonderful. So you can get stuff on Wolfram U. If you really like what we do, go ahead and buy a copy on Amazon. I don't actually necessarily ask you to do so, but those are really beautiful books. And I think when you learn something so well, why not have a copy for yourself? So my answer is, in some sense, everything is there on the Wolfram U course, but not. We can also buy books. Okay, right. So I think we're getting close to the end of our time. We do need to go to Adam stuff. So I'll probably close in just a minute or two, but let me see if there's anything else coming up in terms of questions. So let me just send the chat now. Okay. So in the Q&A, I think I took care of most of it. Okay. So do go to Mark's talk this afternoon. Do go to Adam's talk right after this. Itai's talk on application, which is a very nice talk. All these talks are excellent. So thank you very much to all developers, to all of you. And I'll wait for a minute just in case I didn't cover any question or you still have something more to ask me. Okay, quick question. Oh yes, from Garcia Marina. Quick question, is there a book for the complex analysis course? Yes. Historically, we would do the course first and then not write a book at all. For complex analysis, we actually wrote the book first and then did the course. So the book should appear within a month or two. Book publishing is much more for a subtle art. There are much very different things to do. We're still getting used to it, but we have an excellent Wolfram Media team. So my answer to the question is yes, there is a book on complex analysis which is ready. There'll be a book on PD, special, etc. So all that should be available soon. Okay, I think I've answered everything. Maybe I'll wait a minute or two more in case we still have time. Yeah, so do go to the Wolfram course, do look at the books, etc. Try a new stuff when 14.2 comes out. Let us know what you need from us, and we'll be happy to put in more games or more anything that you really think is useful for you. Okay, looks like we're at 10:30, that CT, which is the time to stop. So I'll let people go to the next talk. Thank you very much for coming here today. It was a great pleasure to talk with you. We can end over here. Thank you.